change something? Okay. You were able to do some magic, I think.
Can you change the slide? I'm not sure if it's really working or, but I see this slide in YouTube.
Yeah, I think it's working. Okay. Yeah, you can see my cursor, right, on YouTube. I can see it at least. Let's wait for some time so that more people can join. Yeah, I'll wait for a couple more minutes. Okay, I think let's get started. Maybe some seminar students are watching on YouTube. It's okay for this lecture, I think, but if you're enrolled in the course, you can use the Zoom link, and that's much better because at some point you will need to participate. Maybe not in this particular first lecture because we're going to talk about some basics, motivating basics plus the course logistics. Okay, so let's get started. Hopefully you're here for the seminar in computer architecture. I think some of you have taken the digital design and computer architecture course that I taught last year or the previous year, but some of you may not. So what I will do in this class is first go through some introduction and hopefully motivate why computer architecture is really exciting today. That's going to be lecture 1A. I'm not sure if I would like to cover everything that I have because it will take some time. I'm going to skip a lot of slides, and I will point you to some other lecture if you really are interested in learning more and going into actually covering all of these slides because we don't have enough time. And then we will hopefully spend some time in lecture 1B, which is going to be the course logistics. Does that sound good? Okay, hopefully. Okay, so let's get started. Let me introduce myself. I'm a professor at ETH Zurich. I've been here for about 5+ years now. Before that, I was a professor at Carnegie Mellon University. I still have one PhD student left at Carnegie Mellon. And I got my PhD from UT Austin and worked at many companies, as you can see, and we closely collaborate with quite a few of them right now in our research also. So hopefully I can give you some industrial perspective as well in this course. You can reach me with this email address. You can find a lot more information on my website, etc. Basically, I do research and teaching in computer architecture, computer systems, hardware security, bioinformatics, and you can see some of the topics over here. In fact, some of the papers that we're going to read in the seminar and analyze in the seminar are going to touch upon a lot of these related topics, because this is a wide variety of topics in computer architecture, especially memory, hardware security, fault tolerance, hardware software cooperation, and architectures for emerging and important applications like bioinformatics, health, medicine, ML, AI, let's say. Let me give you an overview of the research that we do in my group and introduce the group a little bit also, because essentially a lot of the group are going to be the mentors for people who are going to present in the seminar. So our goal is to build fundamentally better architectures, and hopefully I will give you why this is exciting. We work in these areas that are listed on the top over here. And we're following four major directions today: fundamentally secure, reliable, safe architectures, fundamentally energy efficient, memory-centric architectures, fundamentally low latency and predictable architectures that provide quality of service, and architectures for emerging and important applications, as I mentioned earlier. And these span clearly many applications, but they're not limited to these applications that I mentioned over here. If you have taken digital design and computer architecture, you know that we've started the lectures with transformation hierarchy. And this is how problems get solved, right? In the end, our goal in computing is to solve problems. And problems get solved by electrons in dominant technologies today. And we need to somehow communicate the problems and the solution methods to the electrons such that we can solve problems and generate insight so that we can have better lives, right? But this requires us to go through a transformation hierarchy, at least in the general purpose computing domain. This transformation hierarchy may differ in more specialized computing domains or more reconfigurable devices also, right? But basically, computer architecture is really about the hardware-software interface and the microarchitecture in its narrow view. This is the ISA and the microarchitecture that implements the ISA in the narrow view. In this course, and clearly, as I mentioned, in digital design and computer architecture, we take a more expanded view of computer architecture that looks at algorithms to devices. And this is because that enables the highest energy efficiency and performance if we can consider algorithms to devices and optimization across them, basically. Hopefully, I'm going to give you some examples of this, but if you've taken digital design and computer architecture, some of these slides may be reminiscent of what we have discussed. We would like to co-design across the hierarchy, fit the algorithms to the architectures, fit the architectures to the algorithm, and do both actually, so that we can be extremely efficient and specialized, so that we can achieve design goals. So these are some research topics that are happening in my group. I'm not going to spend any time in the slide, but essentially this is what I just mentioned is the type of research that we're doing in my group also. We're doing broad research spanning applications, systems, and logic with architecture at the center. So computer architecture is very special, I think, because you're really at the center of the stack, which means that you enable the algorithms to take advantage of the devices. You enable new devices to be taken advantage of by algorithms, and you enable efficient communication across the stack, if you will. And I picked the algorithms, but you can pick languages, you can pick system software, you can pick microarchitecture and logic also. Basically, you enable that efficient communication, essentially the efficient building of the computing platform, because you're really specially located in the stack. At the algorithmic level, you may not be able to do that clearly, right? Or at the device level, you may not be able to do that. So hopefully this is exciting to people who are taking this course. Okay, so this is my research group. You may, well, at least virtually see some of these people who will be your mentors. And if you're interested in what's going on in the group, we have released a newsletter recently in January that covers a lot of interesting topics, including some papers that we may actually read in the seminar, because some of the papers that we're going to read in the seminar are going to come from our research group. So this is, let me talk a little bit more about my philosophy so that you can see how that affects this class and maybe future classes that you may consider taking, like the computer architecture graduate class. But I strongly believe that teaching drives research and research drives teaching, and this is an endless loop. Teaching drives research because in order to innovate, you really need to know about fundamentals, and you need to have the ability to critically think about them and do better trade-offs and come up with creative ideas to enhance the fundamentals. That's how teaching leads to research. And research drives teaching because once you actually figure out those new ideas, they become fundamentals of the future, right? And I think these are two sides of the same coin. Essentially, teaching is about educating or delivering information about something that's known to many people, to others, whereas research is about delivering information about something that's not known to anyone other than people who have discovered it, right? And after some time, of course, that information gets known, and that becomes, if it's important enough, that becomes fundamentals. So I think this is really important. I believe in this, and that's why I think I consider all courses that I teach as things that could potentially change how things are done as well. But of course, it's important to learn the fundamentals. So especially in this course, but also in other courses, we focus a lot on insight and new ideas and the trade-offs related to the ideas. And I'm very encouraging of new ideas. So clearly, we're going to cover a lot of ideas during the course of this course. And I encourage you to build upon those ideas, come up with better ones, come up with better solutions, and communicate them, because those may be the new ideas of the future. Who knows, right? And again, in this course and research, we focus a lot on learning and scholarship. That's important. We're going to criticize papers sometimes related to this aspect. And I think critical thinking in general is about all about learning and scholarship. And this is something important, I think. I think this applies to the seminar course, all courses, and the research environment. Hopefully, we can have an environment that values free exploration of ideas, openness, collaboration, hard work, and creativity. Okay. And I think learning and scholarship is important because I truly believe in what's written over here. The quality of your work defines your impact in the world in general. Again, you may have seen some of these actually. You've taken lectures from me if you've taken digital design and computer architecture. But if you're interested in some of the research that's going on in the group, there's a lot of a wealth of material out there. These are some of the talks that I delivered, but there are also talks that my students have delivered. If you go to our YouTube channel, you will be able to find them relatively easily. And if you're interested in more views that I have about computing research and education, you can watch this interview that I delivered with the students who were interested in doing this interview. And they asked really good questions a couple of years ago, 1.5 years. And there's more material if you want to know about my thoughts and suggestions on research, especially on teaching and education. You can find them here. Okay, so actually this course and similar courses may be heavy. And I think a lot of people who are taking this course probably know that this is a bit more heavy than other seminar courses, but you will learn a lot in the end. These are some of the comments that we received. Usually the comments are quite positive. And I think they will be more positive if you approach the course the right way as a formative experience, as opposed to something where you will just get a grade on. Because I think if that's the way you approach it, it's not that interesting, I think. Another comment was high investment, high return, and that's probably true. Although I think this is not as high investment as digital design and computer architecture. That takes a lot more time. Here, I think it's not going to take you as much time, frankly. So I think this course and other courses can be taken as a learning experience. And hopefully this will enable you to do long-term trade-off analysis, and especially the reviewing of the papers and presentation will enable you with skills, critical thinking and decision-making skills that are difficult to get somewhere else. That's going to be different from digital design and computer architecture. Even though we covered a lot of critical thinking skills, it's going to be exacerbated over here because you will have to exercise that critical thinking a lot when you're actually thinking about the papers. Okay, so that was a quick introduction to us and the research group and our philosophy. Now, let me talk about computer architecture a little bit. I know some of you have seen some of these slides, but some of you have not. So that's why I'm going to spend some time on it. But again, I'm not going to go through them a lot, because if I do, then we will not have time for course logistics, which I really want to cover. That's important. Okay, so computer architecture is the science and art of designing computing platforms. Again, this is a broad definition. It covers the hardware, interface, system software, and programming model. And the goal is to achieve a set of design goals. For example, in supercomputers, you want to get the highest performance on Earth on workloads XYZ. We may see similar papers to this. In mobile systems, you want to get the longest battery life at a form factor that fits in your pocket with cost less than some amount and with acceptable or good performance, right? So you can actually have many, many metrics you evaluate your design goals with. And in general purpose systems, it's more like you want to get the best average performance across all known workloads or all workloads you care about at the best performance and cost ratio, right? So clearly there could be many, many different design goals and systems that are designed based on the design goals. And computer architecture is really about enabling all of them. Because in the end, at the heart of the design, you will have to have a computing architecture that works and enables your design goals. In the end, designing these platforms can be quite different. Designing a supercomputer is different from designing a smartphone, for example, but many fundamental principles are actually similar, right? Essentially, that's going to be important, right? And hopefully in this course, we will focus on some of these fundamental principles, but we will also focus on some of the cutting edge topics, as you will see. Okay, I wanted to finish something over here on my other computer so that I can actually log into the Zoom meeting so that I can actually see what you're seeing also. So hopefully everything is going well on the slides, right? Okay, now I did join the Zoom meeting on this other place. Okay, cool. Okay, so I also mentioned that this is science and art at the same time, because it's art because you're designing something that you don't know what workload it will really execute. Even though you may actually design for some workloads, it may actually end up executing many different workloads, right? Who knows? And these systems will be out there for tens of years potentially. Then the question is, of course, how can you adapt to those workloads potentially? So it's really art. A lot of the design choices that we make are going to be a mixture of art and science at the same time. Okay, just to give you an idea, these are some of the platforms. Clearly some of these are obvious, some of these are old, some of these are interesting platforms that you may not have thought of as computing systems, but these are actually computing systems, some of the sophisticated computing systems, edge computing systems, let's say. And there are other computing systems that look like this, right? This is a dream, perhaps, right? I would love to be able to trust a car so that I can ride on it like this, and the car is self-driving. But unfortunately, I don't think I will trust any car at this moment because we have a lot of security and robustness problems in the systems we design. But the goal should be perhaps cars that we can drive like this, right? It's always good to imagine a future like this. And Mr. Bean was actually quite innovative and creative in imagining this, I think, when they actually did that. And then this is a more realistic self-driving car, and it shows you the importance of the computing platform in the back over here. I don't want to have a self-driving car with a data center in its back, clearly, right? And this is a data center, a real data center. And this is clearly a different platform with different goals, different cooling requirements, and more general purpose, clearly, than a self-driving car. This looks similar, but this is one of the fastest supercomputers of the world. It used to be the fastest at some point in time. And it looks kind of similar, but it's designed for a specialized purpose, maximal performance on some scientific applications. Usually energy efficiency is becoming a part of the picture also today in the evaluation of these machines. This is another platform. This is Google's machine learning accelerator. It's called a TPU, Tensor Processing Unit. You can read more about it. In fact, if you take a digital design and computing architecture, we covered the concept of systolic arrays. And this is essentially a systolic array at the heart of it. Right. I'm not going to go through a systolic arrays. You can watch the lectures if you're interested, and if you didn't do it already, or if you want to really watch them again. Clearly, these machine learning accelerators are becoming important. This is another accelerator that does machine learning partly, vision partly, and vision also is machine learning today mostly, not completely. But basically, this is an accelerator that's designed for by Tesla. It is designed specifically to execute the algorithms that they designed for self-driving. I think they call it self-driving computer even. But basically, they recognize the need that they needed their own chips. So they're producing their own chips that are customized for their algorithms and software today, just like Google is doing chips that are customized for their own software training and inference algorithms, etc. So they're building the whole software stack to enable these chips to work well with their algorithms. And this is exactly what I mean by algorithm architecture, a device co-design. Okay, so if you define computer architecture in some way, this is another way of looking at it. It's the science and art of designing, selecting, and interconnecting hardware components and designing the hardware and software interface to create a computing system that meets functional, performance, energy consumption, and other specific goals. There could be other specific goals, clearly. And again, the expanded view is what we're going to focus a lot on in this course. And you're going to see examples of real papers that you can select from and discuss in the seminar that shows this expanded view. So this is something we discussed in digital design and computer architecture, but I think we should discuss it very briefly again. Why do we want to study computer architecture? Hopefully, you're here for that reason. We would like to enable better systems, make computers faster, cheaper, smaller, more reliable. And to be able to do that, we want to exploit advances and changes in the underlying technology and circuits, and also the applications. We want to enable new applications and make existing applications better. And I think computer architecture has been extremely important in enabling many applications. For example, graphics, visualization, machine learning. All of those have been enabled by very high performance computing architectures being present. In fact, I'll use machine learning as an example. If GPUs, graphics processing units, were not there, were not as general purpose enough, machine learning would not be having its, let's say, second revolution today, because a lot of the algorithms that are used to train and do inference using models in machine learning, in neural networks, for example, have been known for decades, let's say, but they were not, let's say, as feasible in the devices that were out there. But folks from, for example, University of Toronto realized that you could actually train and execute these algorithms, these models on GPUs much more efficiently. And that has enabled them to actually improve the algorithms also and make them better. And now we're actually experiencing a second machine learning revolution because the GPUs were extremely successful in enabling the performance required by these algorithms. And I see other applications similarly, like self-driving cars. We just need better architectures and better systems, better platforms for those. And going into the future, better virtual reality, personalized genomics, personalized medicine. We're going to talk about that a little bit more. But basically, I think the future of applications, new applications, depends on innovations in computer architecture. And I think there's enough proof out there that I don't need to talk more about this. And we would like to also enable better solutions to problems. This comes from new applications, but it also comes from better doing better with older applications and older algorithms as well. Software innovation, for example, has been built on trends and changes in computer architecture. There was at some point where, for a long time, actually, general purpose computing performance was growing more than 50%, sometimes 2x per year. And that has enabled a lot of innovation in applications. People started adding features that also enabled a lot of complexity in software, but it enabled a better solution potentially. And this is also happening today in specialized systems, for example. It's easy to get, for example, 5x, 10x performance improvement. And also, we would like to understand why computers work the way they do. Clearly, this is important. Hopefully, when you took digital design and computer architecture, that made sense. Okay, today is, I think, a very exciting time to study computer architecture because industry is in a large paradigm shift. There are many different potential system designs possible. There are many novel architectures being investigated. I'm going to give you some examples of this. And there are many difficult problems that motivate these new architectures and that are also caused by these new architectures, let's say. So clearly, huge hunger for data is motivating new architectures, data-intensive applications. Power, energy, and thermal constraints are motivating new architecture, also caused by some of these issues in technology scaling. Complexity of design can be motivating new architectures, but also be caused by problematic architectures. There are many examples of this. Difficulties in technology scaling, memory bottleneck, reliability, programmability, security, and privacy issues. I'm not going to talk over these. This slide could take a lecture by itself, of course. But there are no clear, definitive answers to these problems. And you will see in the papers we cover also that. And these problems affect all parts of the computing stack. And it really affects the user. There are many new demands from the top. There are many new issues at the bottom. And there are fast changing demands and personalities of users. So essentially, we need to think about the user also. So as a result, computing landscape today is very different from 10 to 20 years ago because applications as well as technologies are different. And every component and its interface, as well as entire system designs, are being re-examined. I'm going to go through the slide relatively quickly because we're going to revisit a version of this slide later on as well. But we have immense heterogeneity in systems today. And that heterogeneity enables a lot of opportunity, but also enables a lot of complexity in the system. So I've already given you this axiom, and let me give you some examples of this axiom. Basically, if you want to achieve the highest energy efficiency and performance, we must have an expanded view spanning algorithms to device and co-design and specialize. Let me give you a historical perspective of it. I think historical perspective looks at things top down and bottom up. And I'm going to merge both of those in the next 3 minutes or so, let's say. So people have actually innovated a lot at the bottom layer. Like we have devices are, let's say transistors, for example, right? Memory devices, etc. That were never imaginable potentially 60, 70 years ago. And people also innovated at the algorithm level, clearly. So we're going to talk about this a little bit. So there's this famous lecture by Richard Feynman, who is a famous physicist who actually cares a lot about teaching, for example, which he delivered 60 years ago, 62, I guess, where he basically said there's plenty of room at the bottom, meaning there's a lot of room to innovate at the device level that could enable a lot of innovation at the higher levels. And he mentioned nanotechnology or something like that at that time, basically direct manipulation of individual atoms that can enable a synthetic chemistry that's much better than what is used at the time. And this talk was used by nanotechnology advocates and researchers to actually improve nanotechnology, which is actually happening right now. But basically, Feynman was interested in possibilities of denser computing circuitry, better devices at the lower level. He basically suggested, in principle, it should be possible to make nanoscale machines that can arrange the atoms in the way they want. And I think one of the examples of this is really what he called swallowing the doctor. It's essentially a surgical robot. It's a very nanoscale robot that can do things in your body, right? And I think things like this are being investigated today. Of course, there's a lot more to go. So I think there's still plenty of room at the bottom. Technology scaling has gone a long way, and it's becoming more difficult. But I don't think this room has been gone. I think we need to be more creative in how we look at technology scaling going into the future. But of course, it's true that it's slowing down a little bit. So as a result, people are writing the papers that look kind of like this. There's plenty of room at the top. If technology scaling ends at some point, which is getting close, then at the top of the computing technology stack, we need to innovate a lot more. At the software level, algorithms and hardware architecture, these folks are arguing. And I think that's true also, because as technology scaling becomes difficult, it becomes difficult to get performance and energy improvements just by doing nothing, right? Basically, you do nothing for a year and the technology scales to a lower technology node and you get better performance out of the transistor and better energy out of the transistor. That's great. And that's not happening as much anymore. As a result, people are co-designing across the stack. So I think clearly it's true that there's a lot of opportunity at the top also. But I will revisit the axiom saying that I agree with both of these, but I disagree that one is more important than the other. I think there's plenty of room both at the top and at the bottom, at the devices as well as algorithms, architectures. At that divide, let's say, computer architecture is at the middle of the divide, let's say. But I think you can do much more so. You can get even more room if you can actually exploit the communication and optimization capability across the top and the bottom. Basically, you can cross that divide between the top part, the top blue part of this hierarchy and the bottom green part of this hierarchy. That's why we have this expanded view of computer architecture in research. And I think increasingly industry is having this expanded view of computing architecture as well. And I'm going to give you some examples. But before I give you some examples from industry, let me give you some cross-layer design examples, foreshadow some of the potential things that you can choose as papers to discuss in this class. So this is one example, more expressive memory interfaces. With this memory interface, you can communicate a lot more for semantic information from your data structures to the underlying architecture. And that way you can enable better optimizations in your architecture because you know a lot more about your data structure. For example, you can communicate the security properties of your data structure, privacy properties. You can communicate compressibility properties, approximability properties, locality properties, etc., etc. And these are some examples from the paper. Of course, these are more concrete properties, but you can imagine other things, right? You can improve cache management. You can improve compression, prefetching. These are more traditional examples of improvements in the memory hierarchy. For example, you can do better non-uniform memory access management if you know more about your data structures and memory regions, for example. And this knowledge that you can communicate could be data types. Today, these are not communicated, unfortunately. Access patterns, access intensity, working set sizes, data use amounts and patterns, different kinds of properties of the data, distinguishing between different data structures, different data pools, private and shared properties, etc., different kinds of locality properties. And you can read this paper for more detail, actually. And this could be actually one of the papers that we discuss potentially. It's going to be on the list. And then you could do this in a specialized manner in GPUs. In fact, we did this work with NVIDIA, and NVIDIA is implementing this locality descriptor abstraction that can enable programmers to express locality in their systems such that the architecture can take advantage of it. So there are many other examples. This is another example from our own research where you can actually distinguish between different error vulnerabilities of different data structures and communicate them, communicate the error vulnerability of different data structures to the system such that you can map these data structures to different types of memory in terms of their reliability characteristics. So I think that's very interesting, and you can read the paper for more detail. And this is more recent work where we look at, again, knowledge of how much you can approximate different data structures in a neural network or inputs and outputs in a neural network. And based on that knowledge, you can map the data that's more tolerant to errors to much more aggressively reduced latency and reduced voltage regions of DRAM, such that you can be much more quick in that execution, but you may have some errors, but you can tolerate them. And for data structures that can, where you cannot tolerate a lot of errors, you can map them to more regular latency and regular voltage regions in DRAM. And that way you can actually improve your energy efficiency and performance significantly. And similar things you can do by co-designing software compression and hardware acceleration mechanisms for compression so that you can improve sparse matrix vector multiplication as done in this paper. And also you can actually do even more interesting or forward-looking things, let's say, where you rethink the complete virtual memory interface in a different way by providing more information about the software aspects of virtual memory and having a better interface and doing more things with that information inside the hardware such that you can actually overcome some of the bottlenecks in virtual memory. So some of these papers will be on your reading list, but they're all examples of hardware software co-design such that you can actually improve performance and efficiency and improve scalability at the same time. Okay, now let me give you some examples from real world issues that are having some industry impact. And I will start with some of them. We don't have time, so I'm going to go through quickly on some of them. This is one example. This was introduced in 2019. This is Intel's 3D X-Point technology in the memory. It's non-volatile main memory, essentially. It's based on phase change memory technology. And essentially, this is real today. You can replace your DRAM DIMMs with this memory module, and you can have non-volatile main memory. Of course, this may require some system modifications. Again, this requires hardware, software, co-design to enable something like this. And if in order to be able to take advantage of this non-volatility, meaning that you don't lose data when you power this memory off, then you actually may need to redesign some of your system software and as well as application primitives. But I think this is quite exciting because this was not there until 2 years ago, right? And it's based on phase change memory technology. And this is some technology. And these ideas, just to give you an idea, we're going to cover some papers in this lecture. And you may immediately wonder why an idea is not implemented. There are many reasons for this, clearly. So, for example, for this phase change memory technology to be enabled, there's a lot of device level work that needs to be done. There's a lot of circuit level work that needs to be done. There's a lot of robustness analysis. And then there's a lot of architectural work that needs to be done. And there's some system software work and application work that needs to be done also. So it spans across the stack, clearly. So, but papers can come much earlier than that, right? For example, this is our envisioning of phase change memory. At the time we worked on it, we're still working on it, but we were one of the first in the architecture community working on it, starting from 2007 or so. We basically were looking at how to enable phase change memory as a scalable DRAM alternative. And we wrote the paper, and this may be one of the papers that we end up covering in the end. I'm not sure. Or maybe some paper that builds on this paper. But the idea was published in 2009, as you can see, whereas the product happened in 2019, for example. So it takes a long time for some of these ideas to actually get published. And if you're interested, there's another version of this paper that's more accessible to the public. Okay, so we can actually have more brainstorming on this topic, but I'm going to go through this relatively quickly again. If there are some questions, maybe some TAs can handle it over I cannot see the questions, unfortunately, on my screen. But let me jump into something similar in the sense that it's hardware software co-design completely, but it's completely different. Basically, this is Cerebrus's wafer scale engine that was announced in 2019. And let me look at the right side of this figure here. It's the largest GPU at the time. It's 21.1 billion transistors. That's a lot, actually. it's almost 800, it's almost 1,000 millimeters square, as you can see over here. But this wafer scale engine, which is built to accelerate machine learning training and inference tasks, because it was important by the Cerebras company, which is a startup, has 1.2 trillion transistors. And you can see that its size is more than 50 times the size of the GPU. Essentially, they said that we want this computation capability and this memory capability to be together so that we can actually accelerate these tasks without the data movement bottleneck and have a lot of computation capability close to huge amounts of memory. And this was their solution to the problem. Now, this is nice. You have huge amounts of SRAM, very close to many multiply and accumulate units that can do matrix multiplication, which is important in machine learning, clearly. But of course, this comes with challenges also, right? This is a wafer. Normally, you cut the wafer into pieces and you get things like that look like these GPUs. Now your system, your chip is the wafer. And as a result, you have to cool it, you have to power it, you have to make sure it's reliable, you have to make sure communication latencies are not too high when you're communicating, etc., etc. There are many issues over here that need to be solved, but these are real today, and people are actually building software stack. They've actually built the software stack, like the compilers and the programming models, so they can execute machine learning training as well as inference workloads on it. So I think it's fascinating that people are doing this. And I think this is one example of near memory computing engines. So I see one question: does this persistent memory have a way to reset it like regular RAM? Otherwise, you'll be able to be in trouble. Yeah, basically, the short answer is yes. There are some system software mechanisms that enable you to do that. But yes, that's important to be able to reset it completely, right? But that may take time, of course, also. Okay, now let's go back to Cerebras. Okay, this is one example of specialized engine. It again cuts across the stack, right? Another example, this is processing in memory in DRAM from a company called UpMem. These folks basically put essentially simple processors next to a bank in a DRAM chip. So basically, your computation can be done in these processors. There's a programming model. You write using that programming model. You can optimize your programs, etc. Again, this is another example of optimizing across the stack. And we actually have access to these, and we've done studies. Juan can talk about them at some point. I don't think our paper will be ready for this seminar, but if someone takes a seminar for next semester, they may actually read and analyze the paper as well. But this is actually a sophisticated engine also that designed to minimize data movement. And because now you're not moving the data to the computation units in the CPU, you have computation units inside the DRAM, right? Okay, so these are all very interesting. I'm going to give you another example from just last week. This was announced by Samsung. This is their press release, as you can see on their website. They basically said they built a processing in memory architecture where they can accelerate essentially machine learning applications. But if you look at their instruction set, if you can actually take advantage of those instructions in other applications, you can also accelerate other applications, right? So I think this is quite exciting. And they claim that they can reduce the energy consumption by more than 70%, which actually could be reasonable because you're not moving data as much. If you know what you're doing, that number could potentially be correct, I think. Of course, you need to optimize and depends on what kind of workloads these are. And this is an example of a 3D stacked architecture. I'm not going to go through the details. If you're interested, there's a 2-page ISSCC paper that talks about it. Relatively cryptic, let's say, but I mean, if you understand what's going on, you can understand what they've done. Essentially, it's a 3D stacked system, and you have some logic incorporated into some of these layers that can do what they call function in memory. And what they call function in memory are these example functions, for example, floating point add, multiply, accumulate, multiply, and add. Okay. And this kind of looks like a computing unit on the, like an accelerator, essentially. You have an execution unit on the memory side that is a small pipeline that is relatively specialized. That has some registers. It has some access to registers. It's relatively specialized, basically. Again, I'm not going to go into details, but this is real. And this is an instruction set that you have for this version of their computer. And this is the real chip implementation. So this is happening today, as you can see. And again, keep in mind that papers related to this were written a long time ago. In fact, the first paper on processing in memory comes in general purpose system comes from 1970. Now, I don't have it over here, but we may actually read it in the last iteration last incarnation of the seminar course, we actually covered that paper. I may actually put it so that we can cover it again. I usually try to change the papers so that we have some overlap, but we don't necessarily have overlap. But we may actually read that paper. But we also have papers that are similar, more similar in nature and conceptual idea to what is described over here. For example, you have a specialized accelerator in the logic layer of 3D stacked memories that can do specialized operations, maybe more capable than what Samsung built over here. But it only takes time for these things to become more capable. Research usually is earlier than products, as you can see, by years or decades. So there's one question over here. Would it be possible to use ultra low power RISC-V cores for things like this? And in the end, my argument would be yes. So if you actually look at this paper that I show over here, the scalable processing in memory accelerator for parallel graph processing, we use very simple low power cores. They're not RISC-V cores because RISC-V was not really present at that time because we did this research starting in 2013, but they're ARM cores, but there's no reason why they cannot be any other ISA as long as the cores are really simple. So, and then there are other simple processing in memory approaches that we have been working on, and some of these actually may end up being papers that you choose from. We also looked at real workloads and how they can benefit from processing in memory. And we will include some of these papers, clearly, maybe not all of these papers. But if you end up being interested in any of these papers, feel free to send us a message also. Even if we don't include them for whatever reason, you may suggest them. But again, let's see. So clearly, you can do in-DRAM processing, in-DRAM bulk bitwise execution. And this is an ongoing area where we're working on. We have an upcoming paper in ASPLOS in a month that talks about bit serial SIMD processing using DRAM. And we have an upcoming paper next week at the HPCA conference that talks about synchronization for near data processing architecture. So there are a lot of issues in processing in memory, clearly, which we may cover actually with some of the papers in this course. There's this long primer that we wrote. Hopefully it's accessible. It's easy to read primer that we wrote on processing in memory this December that covers the state of the art in processing in memory essentially and some of the open issues. So if you're interested, I recommend looking into it. And if you're really interested in more of a lecture on this topic, I would recommend looking at this IEDM tutorial that I delivered in December. IEDM is the leading flagship conference. It's the Electron Devices meeting. A lot of new devices get introduced in this conference. For example, I think when people started looking at phase change memory, STT-MRAM, they introduced it first in this conference. So a lot of low-level innovation at the bottom started appearing in this conference. So they're also interested in memory-centric computing systems. And they're also extremely interested in bridging the gap between the algorithms and the devices. And yeah, that's the link to the video if you're interested. And some of you may have taken, I think there's a very small fraction of you who may have taken computer architecture course that we taught last fall. I'm not sure. But if you have taken it, clearly you know that we've covered a lot of computation memory, processing in memory lectures. But if you have not taken it and if you're interested in it, you can feel free to take it next semester in the fall. But you can also watch these lectures individually if you're interested. And there's a lot, as you can see over here. Okay, so I've already mentioned that other innovations are happening in industry. This is Tesla's self-driving computer, as they call it. Clearly, this is a machine learning and vision accelerator, which has other capabilities, some general purpose capabilities, of course. And they basically just found out that they have to design it. They cannot trust the capability of chips that they can buy from others. They have to design this chip such that they can specialize it for their workloads that they're executing on their self-driving cars. And clearly, they have some redundancy capabilities you can see that enables safer operation, etc. If you're interested, you can watch their video. They actually have a very nice description of this at a high level, at a reasonably good level, actually, for a company where the chief architect discusses what they've done in these chips. And I've already mentioned Google TPU. And if you've taken digital design and computer architecture, clearly we've covered at least the core fundamentals of it, which is a systolic array. There's a second generation of the TPU, which is much more powerful. It has more chips. It has high bandwidth memory. Samsung built the function in DRAM on top of high bandwidth memory, so it could be more easily adoptable in these devices also, as you can imagine. It has more powerful floating point operations. It has more powerful processing capability. And it's also, for this reason, it can do training and inference, as opposed to just doing inference. And clearly, companies like Google, Microsoft, etc., traditionally software companies are designing these systems chips. So they're not just software companies anymore. They're software hardware companies at the same time. And clearly, Tesla is not a car company anymore. They're designing the entire system that goes into a car. Okay, so we've already discussed systolic arrays in digital design and computer architecture. We may actually talk about some papers related to systolic arrays in the seminar course also, but some of you may know how it's working. I'm not going to talk about that in detail, but it's essentially a big matrix multiplication unit. You can see that there are 64,000 elements per cycle, matrix multiplications that happen per cycle. And then on top of this, you can accumulate. So you can do floating point multiply and accumulate in this systolic array. And this is just the first generation. Next generation may be bigger. And then, of course, the rest is really system design. So this core innovation is not really an innovation, right? It's systolic arrays have been known for since 1970s, late 1970s. In fact, they were designed and employed for vision processing, image processing at CMU by H.T. Kong and his students at that time. Now, nothing has changed in a sense. These systolic arrays are being employed for convolutions, which they were designed for actually initially, and other networks also. So the fundamental principles are the same, but how you actually use them in the system actually is very interesting also. So you need to actually make sure that the data arrives at the right time. And that's the responsibility of the software and the system design and the firmware to enable that. Again, I'm not going to go through this. This paper may be one of the available papers, or some paper like this may be one of the available papers that we discussed. And clearly, many other AI ML chips are being designed today. Almost all major manufacturers are designing their own ML MI chips. And when I say manufacturers, these are manufacturers of software also, not just manufacturers of hardware. And this is an example of the AI chip landscape from this website. If you're interested, you can take a look at it. And I think this has grown because this example is from a couple of years ago. Okay, so we talked about performance and energy, and I think that is driven by these designs. Let's talk about reliability and security, which is a completely different aspect. So we're going to cover reliability and security in this course. There will be some papers that you can choose from. And this is critically important also. So probably many of you know about Rowhammer. I guess how many of you know about Rowhammer? Maybe you can raise hands or write something. I don't know if I'll be able to see them. So I can see the raised hands more easily. So I can see more raised hands happening. That's good. So a lot of people know about Rowhammer. I think a lot of these folks are folks who've taken digital design and computer architecture. Some people say, oh, heard about it. That's good. Basically, if you're taking digital design and computer architecture, clearly we covered it in the first couple of lectures. But this is a system security vulnerability that's happening because of technology scaling issues at the lower level. I'm going to go through this relatively quickly, but we may actually cover some Rowhammer papers. Traditionally, in the seminar, there were Rowhammer papers covered, starting from the fundamental Rowhammer paper that we have written in 2014, but more recently, recent attack type of papers that are really quite interesting also. But essentially, Rowhammer is a phenomenon that you can predictably induce bit flips in commodity DRAM chips. And at the time we tested these chips, more than 80% of the tested DRAM chips were vulnerable to this. And this is really the first example of how a simple circuit level hardware failure mechanism can create a widespread system security vulnerability. And you've probably seen this if you've taken digital design and computer architecture. Basically, folks are writing more popular articles that say, forget software, now hackers are exploiting physics. And I think this is a very good high level, let's say, induction into Rowhammer, because it's really about physics in the end. It's really about how different transistors and different physical structures affect each other. The noise in one structure affects the noise in some other structure. And as a result, you get a bit flip. And then you can exploit this bit flip in software. Okay, let's go into a little bit more detail. Basically, in modern DRAM chips, you have many rows. If you want to access a row, you need to apply high voltage to the row that you're accessing. Let's call this a opening of a row. If you want to access some other row, you need to apply low voltage to that row. So you close the row, basically. Let's call this open and close. In DRAM, there are specific terms, activate and pre-charge. Now, assume that you keep doing this repeatedly. Open, close, open, close, open, close, open, close, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, voltage. Enough times before the cells get refreshed. It turns out in most modern DRAM chips, if there are vulnerable cells in physically adjacent rows, they basically flip. They can flip from 1 to 0, 0 to 1. If you actually go into Rowhammer in detail, you will see why it's 1 to 0 and why it's 0 to 1. But basically, we call this the hammered row. We call these the victim rows. And we basically show that repeatedly doing this hammering enough times leads to errors in more than 80% of the chips that we tested at the time. And these are 3 major manufacturers, ABC. Samsung is one of them, Hynix is one of them, and Micron is one of them. And there are only 3 major DRAM manufacturers, unfortunately, today. It'd be good to have more innovation in the field. But it's good to see some companies are finally looking into processing in memory and actually releasing products. Maybe a bit later than we would have liked, but it's a progress in the right direction, as you can see. But basically, these errors happen because they're technology scaling problems. So there's one question over here. Is it possible to do a row hammer attack using only C and assembly? And the answer is yes. So I'm not going to go through this in here. You can watch some of the row hammer lectures. But when we actually wrote the paper, we also released a 5, actually it was at the time 6 instruction assembly code that induced these errors. And Google later improved that assembly code and made it better so that they could actually induce more bit flips. So the answer is yes. And I'm going to show you some high-level examples, not the code over here. But basically, when we first started looking at the problem, we tested chips from 2012 in 2012 and 2013. And we basically showed that more than 80% of the chips are vulnerable. And we basically said that this is a security problem and reliability problem. This should not happen. Memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses, because someone can exploit it to hijack your computer. And later, Google Project Zero folks showed exactly that. They basically exploited this row hammer bit flips as a user level program to take over the system by breaching memory isolation and getting access to the page table of the program such that you can modify the page table. So hopefully that's interesting. Anyway, I'm not going to talk about this because we're going to read more papers. And again, I'm going to refer you to some lectures. But one famous hacker mentioned this on the internet when they heard about and examined row hammer. They said it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. And this is a beautiful analogy, I think, of row hammer. It's essentially about disturbance. Whenever you're hammering one row, you're actually causing disturbance to the cells around that row, because these cells are too close physically. And also these cells are too small physically. As a result, they're vulnerable to these disturbance noise that's created by the hammering that happens of these word lines. And your hammering means changing the voltage repeatedly many, many times on this word line, right? So this is going to become a bigger problem. So given, let's see, given that you know to address A, B such that A and B maps to different rows. Yes, exactly. Basically, there's a lot that goes into a row hammer attack, which you may actually read about if you choose to study some of the row hammer attacks papers that we are going to release as example papers. But this is one example paper, for example. These folks from TU Graz showed that they can gain unrestricted access to systems of website visitors by inducing row hammer bit flips using JavaScript. These folks from Vrije University in Amsterdam showed that they can gain control of a smartphone deterministically using an Android application that's running on Android at the user level. Again, I'm not going to go through the details, but these papers are published in some top security conferences, you can see. These folks showed that you could do these row hammer attacks much better in GPUs and exploit them through the WebGL interface in a mobile system. These folks show that you could do these row hammer attacks through the on remote machines using the remote direct memory access interface. And these folks show exactly the same thing in a different way. These folks show that you can leak private information using row hammer hammerings, let's say, even if you are not able to take over the system. These folks show that, along with these folks, you can do row hammer attacks on deep neural network inference engines, and basically you can deplete their intelligence, meaning you can reduce their accuracy from something reasonably accurate to almost not accurate at all, right? Because you're causing row hammer bit flips in the system. And I think, imagine that you have a self-driving car you rely your life on, and or somebody else relies that your self-driving car drives nicely. So you really require very high accuracy. But if you actually are vulnerable to this reliability issues or security issues, because the reliability issue can reduce your accuracy, the safe, or someone can attack you such that your accuracy is reduced, then you have a huge problem, right? Basically, the inference accuracy of all of those sophisticated algorithms can be degraded to much worse than a random guess. I would argue that 10% is much worse than a random guess potentially in some cases. So, okay, so that's why this is important, I think. If you have fundamental problems with technology scaling and your infrastructure, that can have a huge problem. Somebody wrote a nice message saying that you can also reduce the intelligence of a human by hammering their head. I agree, yes. In a sense, it's not that much difference over here. You're hammering the chip. Okay, so if you're interested in RoHammer, this is something we may put on. I'm not sure. This is actually an old paper by now, but it's a very fundamental paper. It's 7 years old. We wrote this retrospective paper with one of my PhD students, Jeremy, who's going to be one of the mentors here on RoHammer issues. And there are some very exciting things that have happened to RoHammer in 2020. We have written some papers that have had significant impact in the field, like this one, where we show that RoHammer is becoming much, much worse today. You can actually induce bit flips after only 4,800 double-sided hammers, which is really bad because in the first paper that we wrote in 2014, that number was 139,000. So there's a huge drop in the number of hammerings that you have to do to induce bit flips. So technology scaling is getting worse, basically. And there are a lot of other interesting results in this paper. In this paper, collaboratively with folks, we showed that the in-DRAM mitigations implemented by the manufacturers are actually not secure. So manufacturers implemented some mitigations. They basically claim that they're secure, and they declare their RoHammer chips RoHammer free. And a lot of folks believed them. We didn't believe them as researchers. We basically investigated the issue, and we're still investigating the issue. And we basically showed that you can circumvent these RoHammer protections, let's say, that are put inside the chips because they're not secure enough, essentially. And we can cover this paper potentially also. And then there's another paper where we look at whether you can actually declare RoHammer, declare DRAM chips as RoHammer free or not. And I think that's a very difficult problem for testing going into the future. But there's a lot of interesting insight in this paper. Okay, so clearly there's more research going on in this area. Their solutions are going to be increasingly important. And based on the papers that we cover, you can always actually come up with new ideas potentially. And this is one new idea that we're going to present next week at the HPCA conference that provides a low-cost solution and a secure solution to RoHammer that doesn't require changes to existing DRAM chips and that doesn't require knowledge about the internals about a DRAM chip. So this could be one of the papers that we cover about RoHammer, for example, if people decide to select it as a paper that they would like to present. And I think solution space is going to be more interesting. Interesting computer architecture, if you find out at the end of this class that you really want to work on computer architecture or learn more about it, I'd recommend taking the master's level course that we offer. Again, it's also an intense course, but you'll learn a lot. And there are a lot of extra credit opportunities. So if you're actually really interested, you can learn a lot in the course. Okay, that was RoHammer. Very quickly, there's also, it's not just about RoHammer, it's also about other security vulnerabilities that are increasingly more, let's say. So it started with Meltdown and Spectre. So RoHammer was early. Meltdown and Spectre came out in late 2017, early 2018. This is a fundamentally different type of vulnerability because RoHammer is a physical vulnerability, right? It's a circuit level vulnerability that leads to a bit flip, and then software becomes vulnerable because those bit flips directly impact your data structures in memory. Whereas Meltdown and Spectre is a microarchitectural level vulnerability where because of the design of the microarchitecture, you can extract information that you're not supposed to have access to. So basically, someone can steal secret data from the system, even though your program and data are perfectly correct. Your hardware behaves according to the specification, which is not true in RoHammer, but it's true in Meltdown and Spectre. In RoHammer, hardware is not behaving according to the specification. The specification says you should not be able to induce bit flips in that sort of predictable manner. There are no software vulnerabilities and bugs. So why is this happening? I'm not going to go through details, but if you've taken digital design and computer architecture, you have a lot of the ammunition that you need to know to understand why this is happening. It's a bit more sophisticated. It's not as easy to follow, and the attacks are not as easy to mount, I will say. But essentially, at the high level, speculative execution due to branch prediction, for example, leaves, or out of order execution of instructions, it leaves traces of secret data in the processor's cache, which is internal storage, as you know. It brings data that's not supposed to be broad accessed if there was no speculative execution. And a malicious program can inspect the contents of the cache to infer secret data that it's not supposed to access. And in fact, you can actually make this malicious program more intelligent if you know what you're doing, what kind of microarchitectural structures there are there in the system. Then you can actually force another program to speculatively execute code that leaves traces of secret data. Okay, I'm not going to go through this in detail. It's actually fascinating to read about this, and I will recommend you to take a look at Jan Horn's blog post about this. There are also clearly a lot of papers, and there are clearly a lot of variants of it right now that talk about attacks that exploit this part of the microarchitecture or that part of the microarchitecture so that they can gain access to privileged information or private information. These are all started from Meltdown and Spectre vulnerabilities. And this is a very rich area of research right now. There's also another aspect of research that looks at voltage and clock frequency based vulnerabilities, which we may also talk about. And there's also some other hardware Trojan based vulnerabilities. Like if someone controls your manufacturing, can they insert malicious hardware into your chips such that those chips can be triggered at the right time so that they can leak private information to the person who has manufactured your chips. So that's another interesting topic today in hardware security, for example. So clearly, these are interesting things that are happening in computer architecture. Clearly, there are more demanding workloads. I'm going to cover these also. I should try to speed up a little bit because I want to talk about course logistics as well. But as I said, applications are increasingly demanding. AI and machine learning is one example. And I think we should dream and applications will come. And this is true. This has been proven over and over. Sometimes you have some naysayers that say, oh, okay, these are the best applications that we will ever have. And I think hopefully those naysayers are in the minority. Clearly, applications can be used for good and bad, like any technology. Hopefully, we will have good applications, better applications, and we'll protect against the bad applications using security and privacy mechanisms that we build into the architectures. But I think good applications would be very useful into the future. But these applications will come because there are a lot of dreamers in the world, and I will encourage you all to be dreamers as opposed to naysayers, because that's a much better outlook into the world and the future. And as these applications push the boundaries, these computing platforms will become increasingly strained. And we're seeing that with AI and ML, for example, right? People were not able to execute the training algorithms until they figured out that they could do that on a GPU. And as a result, because the computing platforms were too strained to execute those algorithms in a reasonable fashion. But now, that's not enough. Even a GPU is not enough because we're very much energy bound. Our models are becoming big. You could, of course, question, is that really the right way to go? But it's happening, and it's potentially the right way in some applications. And now we're building bigger models. Now those are straining the computing systems even more. As a result, everybody is essentially designing accelerators to co-design across the hierarchy. Okay, that's AI and machine learning. But I think some other emerging area that we're working heavily on is genome sequencing. And I think this is really, really important. Potentially more important than AI, frankly. I don't know. At least the current form of AI that people have kind of reduced it into. So I think it's good to distinguish between deep neural networks and machine learning. Machine learning is definitely not limited to deep neural networks, but a lot of these accelerators are operating on deep neural networks, for example. They're not capable of generalizing beyond deep neural networks. For example, reinforcement learning, which has principles that are even bigger than deep neural networks. They're non-supervised networks, learning mechanisms, for example. But again, we need to be, those applications are also upcoming. But I think I'll briefly talk about genome sequencing. This is actually important because we have devices at the technology level that are very, very capable that look like this. You can actually buy this device for $1,000 and start sequencing genomes around you if you're interested. It could be any genome, right? But the processing of the data and asking questions to it becomes much more problematic because they have a huge performance energy bottleneck. So why are these important? Now I can use the slides that I've introduced in the digital design and computer architecture course last spring, let's say, when COVID was outbreaking, let's say, in China at the time, And I put up the slide, if you remember, if you're taking digital design and computer architecture, and said computing infrastructure is going to be even more important. That's why the fundamentals of understanding computing is important. But this is real, basically. People are using these nanopore sequencing devices to really understand what's happening to coronavirus, what's happening to its variants. They're trying to do outbreak surveillance and try to do prediction, etc. So there are a lot of analyses that you can do, but you're limited by performance and energy because these devices are not capable enough today. So you can do even more things if you are actually capable of doing this sort of analyses with good devices. So you could do microbiome profiling. This is based on a study that was done in New York City, for example. These folks went and really sequenced things that they saw in different places, for example, the subway. And then they basically created a map of different bacterial diversity in New York City. I think this is interesting. Clearly, you can understand what kind of bacteria are where. That could lead to some policy decisions, that could lead to some public health decisions. You could make it even more targeted. You could be looking for outbreaks. You could be looking for potential variants, etc. But this analysis is actually quite computationally costly, right? There's a lot of data that you need to gather. There's a lot of analysis that you need to do. There's also the accuracy of the analysis. There's the performance of the analysis. I'm not going to talk about that, but you can look at papers like this. So this kind of metagenomic analysis that span potentially millions and millions of genomes is really constraining the devices that we have today. So this is another example. This is much before the outbreak that we're currently experiencing. This is Ebola in Guinea. And these folks clearly titled their article as real-time portable genome sequencing for Ebola surveillance. And you can see this is the portable, which is not what we considered portable with our cell phones and nanopore. But today we can do even more portable. That's great. And real-time is probably not the real-time that we are thinking of. We are thinking of, for example, every minute. So getting an answer in a minute. But I think this is actually really great to see this sort of applications, and they're going to become increasingly important. And we have many different types of genome sequences, not just nanopore that is used in the previous studies, but also these bigger applications. And they all have their place because some of them are extremely accurate, for example, and they're extremely high performance. They can generate a lot faster and a lot more data, higher throughput data than these smaller devices. So it can actually incorporate computation capabilities inside these platforms also. And because the cost of genome sequencing has been reducing a lot because of the developments in these technologies. So these technologies I see as improvements at the bottom, right? There's a lot of room at the bottom, right? These technologies have been developed because of that room at the bottom. They're really nanoscale technologies in a sense. And I mean, a nanopore is a nanoscale hole, for example. So it's all about the room at the bottom. But in order to be able to take advantage of them at the top layers, we really need to design the entire computing platforms because we're really being overwhelmed by the data that is generated by these devices. Because the cost of these devices have reduced dramatically, as you can see. And you can see that the Moore's law is actually pointed out over here. And the cost of these devices are reducing much faster than the cost of a transistor is reducing today. Okay, so genome analysis today is bottlenecked by the computational analysis that we have to do. And again, we may cover some of these papers. It's an ongoing research topic in my research group and increasingly more research groups across the world. Initially, when we started, there were not a lot of research groups that were looking at these issues. Now there are more for sure, but I think the number is still not as many as the research groups that are looking at machine learning and artificial intelligence accelerators. But as I said, I think there's a lot of opportunity here. And you can see that you can use FPGAs, field programmable gate arrays, to accelerate these workloads. You can use in-memory processing. You can use a combination of algorithm architecture co-design. And this is one of the latest co-designs that we have done with Mohammed, who is actually a lecturer in this course, as you know, that can be executed on CPUs, GPUs, and FPGAs. And you can also improve approximate string matching with algorithm architecture co-design. Damla is also a mentor in this course. And I think the future of genome sequencing and analysis is going to be increasingly more important and interesting, and we will need to build better systems. Let me first very quickly cover this. This is from Nanopore Technology website. So it's a company clearly that will advertise their technologies. They're basically advertising for 7 hours from RNA to answer, of which 1 hour is a sequencing time. So it's impressive. I think that sequencing time is very short. We need it to even shorter, so we need more technologies. But I think analysis time is 1 hour, which is also potentially short here. But I think we need to reduce both of them to lower than a minute. But I think analysis is actually much worse than what's depicted over here. This really depends on the analysis. So if you're actually doing a metagenomic analysis across, a heavy metagenomic analysis across, I don't know, millions of genomes, it's not going to be 1 hour. You'd be lucky, extremely lucky if it finishes in 1 hour. It's going to be weeks potentially, right? Depending on what kind of analysis you do, of course, and what kind of iterations you do. So basically today we're nowhere near real time, even though it's kind of advertised. Of course, Nanopore is quite good today, right? It's the best technology that I know of to achieve this in a portable manner and close to real-time manner, but it's nowhere near what we want. For example, if you want to give this to the hand of a doctor who's there to make a critical decision very quickly, let's say they have only 5 minutes, I don't know, 1 hour to make a decision, this device will not work because with a simple RNA, it takes a very long time, as you can see. So basically, we still need a lot of innovation in this area. And this is also from Nanopore's website, which is actually, I think, nice because they talk about what else can this be used for. They basically say you can do more stuff than what we just discussed. They can basically research potential future treatment implications, identify correlation for risk factors. So basically assess viral genome in its native RNA form and the effect of base modifications so that you can track strains, for example, different sort of strains and different sort of mutations and their effects on potential effectiveness of known vaccines or other treatments. So clearly there are many, many things you can do, but this requires a lot of metagenomic analysis, as it's also mentioned somewhere over here. I cannot find it right now. But basically you can do whole genome sequencing, etc. Anyway, so basically these analyses, there's a metagenomic here. Basically, you essentially, by comparison of many, many genomes, you can learn a lot more, but your computation capability becomes increasingly constrained with that comparison. Okay, so if you're interested, we actually have a survey article that's written. Probably it's not going to be one of the articles that we will cover because it's a survey article. It's a short article, but if you're interested, I would recommend you take a look at it. It covers the state of the art in this field. And this is a recent talk that I delivered that also covers the state of the art that was done last month, essentially. And again, in computer architecture, we go into more. And we also have some project courses where you can do actually hands-on projects on accelerating genomics that we offer. If there's interest after this seminar or during the seminar, or some other year. Okay, so it's not just about genome sequencing. There are clearly many, many other applications. I'm not going to go over these in detail. And these applications are essentially everywhere in our lives, right? Databases, graph processing, data analytics, data centers, they all have bottlenecks in terms of scalability, performance, energy, reliability, and security in terms of data. And on the mobile end as well. And we actually analyze these applications a lot. These are browsing, TensorFlow, video playback and capture, like what we're doing right now. We're consuming a lot of energy right now, for example, because we're moving a lot of data inside our machines, across our machines, etc. So we're bottleneck basically. And we analyze these workloads on a mobile system, and we found out that more than 60% of the entire system energy is spent on data movement in these devices, on these applications, and real data sets. And this is, I think, fascinating. That's why processing in memory is becoming very important, so that we can get rid of the energy, huge energy bottleneck in the systems we have. Okay, so let me give you one perspective why processing in memory is becoming even more interesting. So today a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition, and this is depicted in this figure. These numbers are relatively old. It doesn't matter. The 2 to 3 orders of magnitude remains today. Basically, a 64-bit double precision floating point operation consumes 20 picojoules. A DRAM read or write to access one of the elements consumes 16 nanojoules. That's 800x, right? So the question is, does it really make sense to bring the elements to a processor, CPU, or an accelerator so that you can do this very simple computation today, right? And the idea in processing in memory is really clearly do the addition or floating point multiply and accumulation on the DRAM side so that you don't exercise this heavy interconnect and so that you don't pay the penalty cost of 800x energy increase. So somebody asked, do you mean a complex number addition with, yes, it's basically, well, it's a complex addition. It's not a complex number. It's a floating point number, but it's not as simple as adding 2 bits, for example. It's adding 64 bits in a format that's double precision floating point. So it's not complex numbers, no, but it's a floating point number addition. As opposed to a simple addition, you have much more complexity. So even that complex adder that you build consumes only 20 picojoules, basically. That's the point here. So a simple adder, actually, if you're doing 4-bit integer addition, that's going to be much less costly in terms of picojoules. It could be 5 picojoules, let's say. I just pulled that number out of the hat over here, but it's not unreasonable to imagine that it's going to be 5 picojoules if your 64-bit double precision operation is 20 picojoules. Okay, so clearly we're going to cover a lot on processing in memory depending on which papers you suggest, but this is exactly why processing in memory is happening today. And let me give you a historical perspective very quickly. If you go back 70, 80 years ago, and if you actually look at the cost, relative energy cost of these two operations, you would see a completely different picture. And that picture will basically show you that the addition or double or floating point operation at that time, or whatever operation, let's say, is about 2 orders of magnitude more costly in terms of energy than a DRAM, a memory read or write. Now, what has happened over the course of 70 or 86 years is described in 2 words: technology scaling, or more appropriately, logic technology scaling. Essentially, the adders that we could build became much more efficient, faster, higher frequency, smaller, etc., because we were able to reduce the size of a transistor as much as possible, and its energy efficiency improved over time, over the course of 70, 80 years. But the interconnects and the memory cells did not scale as well, let's say, in terms of energy, especially interconnects. So logic scaled really well due to Moore's law, but interconnects did not scale. As a result, we are now 2 to 3 orders of magnitude worse in terms of memory access compared to addition, let's say. Okay, so hopefully I've convinced you that many interesting things are happening in computer architecture today as late as just 1 week ago. There's one more question. Let's take a look. Is that energy used on the CPU side or on the DRAM side? So basically, the energy that I show over here for DRAM is used on the DRAM side, DRAM and the interconnect. It's not used on the caching side. We're ignoring the caches over here. So if you look at the caches over here, there's also more data in this picture. Basically, a 256-bit access to an 8 kilobyte SRAM array is 50 picojoules. So it's still much lower than 16 nanojoules. So basically, you really need to reduce the data movement from the DRAM side. Of course, you can make 50 picojoules more efficient as well, but you're not going to gain a whole lot, right? Of course, this depends on the size of the cache also, so I should not be unfair. So for example, if you actually go through the entire chip, I believe it consumes 1 nanojoule or something like that. It's not depicted over here, but you can find another version of this picture later on. Okay, so basically today there are many novel concepts are being investigated: new computing paradigms, new accelerators, new memories and storage systems that I mentioned earlier. And we have increasingly demanding applications and increasingly diverging and complex trade-offs. So this is the 1 nanojoule that I mentioned. If you go from this part of the chip, this part of the chip, that interconnect costs you 1 nanojoule. So the memory, the array access for SRAM is actually relatively cheap in terms of power. Okay, I've already said this, and this trade-off is new, relatively new, and it's becoming much worse. So past systems look like this. Newer systems are increasingly more heterogeneous, as you can see over here, and increasingly complex as a result. All parts are heterogeneous. The processing units have many different types of processing units. Even inside a simple core, you're both dynamically and statically heterogeneous. There are different types of cores, there are different types of accelerators, and they use different frequencies and voltages at different times. Memory is becoming heterogeneous, as you can see. So basically, we have massive amounts of heterogeneity. As a result, the landscape of computer architecture is very different from 10 to 20 years ago. Today's applications and technology demand novel architectures. And today, because of this, every component and its interface, as well as entire system designs, are being re-examined. So this is another version of the slide that I showed you earlier. So I will conclude with this because I think we are going to read a lot of papers, and it's always good to innovate on top of them also. It's good to realize that you can revolutionize the way computers are built if you understand both the hardware and the software and change it accordingly. You can actually, today is a good time to invent new paradigms for computation, communication, and storage. So for example, when we started working on processing in memory, that was our goal. And I think our goal is partly achieved, but not fully achieved at this point, because industry is now taking it seriously. Even a company like Samsung is putting out processing in memory designs, right? I think they need to be more aggressive, maybe similar, even more similar to the aggressive designs that we have been envisioning. But I think it's a matter of time. that they will come to that. But of course, there are a lot of problems that need to be solved going into the future. So I will also recommend this book that I recommended, I think, in digital design and computer architecture, which is The Structure of Scientific Revolutions, which basically analyzes how scientific revolutions happen. Basically, in pre-paradigm science, there's no clear consensus in the field in terms of what is the best way of designing things, what is the best way of explaining a phenomenon. In normal science, you have a best way of dominant theory that's used to explain the phenomenon or do things. Exceptions are considered anomalies. Today, we're in the revolutionary science or engineering period where we're really re-examining underlying assumptions we make in the systems. And I think processing in memory is a really great example of this. Basically, you have this example that I showed you over here. Today, we're designing processor-centric systems. We're moving a lot of data around. That's causing a lot of energy inefficiency, a lot of performance problems, a lot of scalability problems. So it's the right time to examine the underlying assumptions so that we can build some new consensus in the field that can enable better systems. So, okay, that was a very quick introduction to Thomas Kuhn type of analysis of computer architecture, but there's a lot more to be said, but I don't have time to say more. You can read this book. I would really recommend reading it, actually. It's a really great book that talks about how these scientific revolutions happen. And it also talks a lot about human psychology as well, in terms of how science is perceived and potentially prevented because science doesn't work the way either politicians or clergy or other scientists who don't benefit from the new way in which science works. Basically, the science doesn't always work the way they like, other people like. As a result, people are resistant to change. And they could be politicians, clergy, or scientists, or whoever, right? So I think this book is very instructive. And I think this is a good time also because I think today, even in 2020s, we're having difficulties in somehow making scientific decisions in real life, even though we know exactly what the decisions should be based on the scientific principles. But a lot of the times, science is being ignored for a variety of reasons because it's just too convenient. Or usually it's because of dogmatic reasons saying that, oh, this is not right. Anyway, basically, I think today, it's an exciting time to be understanding and designing computing architectures. There are many challenging and exciting problems in platform design that no one has tackled or even thought about before. So you can actually discover these things potentially, and that can have a huge impact on the world's future. So I am hopefully convinced that some bit flip should not be ignored as a simple bit flip because the future really depends on it. And today, part of it is driven by applications from the top. And I think there's a lot more room at the top. Clearly, new applications, every greater realism, huge hunger for data. And we can easily collect more data than we can analyze and understand. So we can do a lot more with that. But also, a lot of it is driven by significant difficulties at the technology layers because the devices are not scaling very well. We need much more energy efficiency, reliability, better or simplicity. Complexity is becoming problems. Security and scalability all becoming problems. Okay, so hopefully that was the introductory lecture. Feel free to ask questions while I switch to my other window that talks about course logistics. Let me see. I need to share my screen. And okay, now I'm sharing my screen. I think there may be some questions on YouTube, but in the future, we may need to have a good way of monitoring questions on YouTube. Maybe we can discuss this in the course TA meeting tomorrow so that we can record some of those YouTube questions such that we can have a good experience, assuming there are good questions over there. But I don't really have reach to actually get to those questions. Okay, any questions very quickly? Please speak up. You can speak up. Okay. Okay, somebody said I can copy the YouTube questions into the Zoom chat if needed. I mean, feel free, yes. If you think that'd be useful, I can try to answer them. But I think in the future, we'll need a more methodical way, unless you're really thinking that you should always be doing that. I think that's a lot of work. Okay. So people can speak up, by the way, if you can turn off your microphone and say you have a question. I don't see anything. Anybody having a question? So George, do you have a question? I see a hand raised. I'm not sure if that hand was raised for an answer, so maybe not. Okay, so let me now cover quickly the course logistics in the remaining amount of time. Basically, with that background, some of it is going to be, it was review for those of you who've taken digital design and computer architecture, but it was not review for many of you, I think, because I think some of you have not taken that course. So hopefully it's interesting. You can learn more about it. But now let's go into the course logistics. So what is the role of this course? This is a seminar course. And basically, we will cover fundamental and cutting-edge research papers in computer architecture. And there are multiple components of this course that are carefully designed to improve students, meaning your technical skills in computer architecture, critical thinking and analysis, and technical presentation of concepts and papers in both spoken and written forms. So that's going to be important. So I think all of these are important. Okay. So hopefully communication is a big part of this. And hopefully you will get familiarized with key research directions. I've already given you an example of it, but by reading the papers in more detail, you will see even more. And hopefully you will be at a position where you could actually develop ideas and innovate. So you will get to a position where you will cover the fundamentals and cutting edge research quickly. Clearly, you should have taken some computer architecture course for this. So our key goal is really this. We would like to rigorously analyze, present, and discuss ideas, papers in computer architecture. And of course, we would like to learn how to do this also, because probably many of you have not done this before. So this may be the first seminar course you've ever taken. As a result, you will learn in the process. So we actually have a structured way of enabling you to learn this process. Okay, I'm going to talk about that structured way, basically. So to achieve this key goal, there are steps that we need to take as a presenter, as well as the participants. So in each session, there's a presenter, and the rest of the attendees are participants. These attendees are both students who are taking the course, as well as people who are in my group. And the presenter basically needs to read the paper, absorb the paper, read more and other related works, critically analyze the paper, think, synthesize, prepare a clear and rigorous talk based on that understanding, present it, answer questions, and analyze and synthesize in the meeting, after, and at the course end also. Basically, they're the leader for the discussion for this, and we're going to enable you to do that. For the participants, basically the key goal is really to discuss, ask questions, and analyze and synthesize during the meeting, after the meeting, and at the course end. So a meeting is important, but we also have forums in Moodle where we will discuss. At the course end, you will synthesize with a synthesis report. So we're going to cover a lot of topics, and we have not fully selected the papers yet. We're going to make them available soon. But clearly, a lot of the topics that I've described are going to be part of it, but there will be more topics. I'm not going to go through this list and describe them to you, but hardware security, you can bet that that's going to be a good component. Clearly, architecture acceleration for new workloads, memory systems, interconnects, processing inside memory, new ideas, new execution models, etc., fault tolerance, reliability, etc. Again, there are more topics to computer architecture than what's depicted on the slide. So to recap, I think broadly, the bigger goals of this course is to teach, enable, empower you to think critically. I think that's important when you analyze papers. Think broadly, because you may come up with different solutions. Learn how to understand, analyze, and present papers and ideas. So communication is a really important aspect of this course. And it will also enable you to get familiar with key first steps in research, because all research starts this way, basically, by reading papers, by discussing ideas, essentially. And also it enables you to get familiar with key research directions. So I actually have a good picture of this. There's a virtuous cycle for scientific progress. You start by reading, critiquing papers, and understanding problems. That leads you to questioning and brainstorming. That leads you to hopefully develop out of the box and new ideas. And this could be a collaborative process, by the way. It doesn't need to be an individual process. And I think collaborative process is a really good process. That's something I encourage everyone to do. And then you can collaborate, work hard to look at the idea in more detail. So this is the hard part, basically, potentially. So enabling a good idea is 1% pearl and 99% sweat. You may have a great idea after 1% of your time spent doing this part, and you may actually spend 99x more time to actually enable and show that your idea is a good idea. So there's a lot of time spent on infrastructure. So clearly, we're not going to do that in this course, right? This course is a seminar course. You're not going to work on new ideas. But it's important for you to realize that there's 99x more work to be done to enable the new idea. And that work actually includes publishing. Well, I guess these two parts, publishing the idea and enabling others to understand the idea. So yeah, coming up with the idea is 1% maybe. Then you enabling that is 99%. Of course, this fraction differs depending on the idea. And then after you do good research and publish, educate others and more, you can keep going through this virtuous cycle, and you enable this virtuous cycle for other people as well, right? Because now you have a important work that is published, and somebody else can take that and feed it into their loop. Okay, so I think that's the importance of scientific progress. Of course, there are a lot of issues that prevent science from working perfectly today. Like sometimes reviewers read papers and they don't understand it, partially because the papers are not written well, but partially because reviewers don't do due diligence to the papers. So hopefully we will also discuss that in the course of this course. Okay, let me go into more logistics. I've already introduced myself, so I'm not going to do that again. These are some of the other folks you're going to work with. So there are two other instructors. They're both senior lecturers in my group, Mohammed and Juan. And there are a bunch of teaching assistants or mentors, we should call them, because they're going to be mentoring a bunch of papers that you choose. Please get to know them and their research, as they will be your mentors. Okay, some requirements and expectations. So I'm going to require attendance for all meetings. If you're going to miss a meeting, please let us know. There's some tolerance, of course. I don't think being extremely rigid works in science in general. So there's tolerance in missing some meetings, but they should not be more than 2, let's say. So each student presents one paper. You prepare for the presentation with engagement from the mentors. And this is full presentation, questions plus discussion. We're going to talk about that. And non-presenters participate during the meeting, ask questions, contribute thoughts and ideas. It's better if they skim or read the paper beforehand. And non-presenters take an online short quiz after each session. There are 5 multiple choice questions for each presentation, and you'll have 4 hours to submit. So usually they're not that bad, I think. If you paid attention during the presentation, basically it's easy. If you have not paid attention, then I cannot guarantee that it's easy. Then you have to sift through the slides to answer the questions. So I would recommend paying attention to the presentation. And everyone comments on the papers in the online review system. This is hopefully a good place to discuss ideas, for example, and other topics that we didn't have time to discuss. At the end, everyone will write a synthesis report, and sample synthesis report is online. You can already find what you're going to do basically at the end of the semester. It's not that bad, I think, the synthesis report. It basically puts your thoughts together. Assuming you've participated, you've done the tasks, it's going to be easy, I think. So course websites, it's linked from here. All course materials are to be posted. Clearly, this is live streamed. You can even watch it on YouTube. Yeah, there are other information. So please check frequently for announcements and due dates, but please check your email also, because we're going to send to your email how we're going to proceed. So Moodle has announcements and due dates, quizzes, paper discussion, and assignment submissions as well. So please check that as well. So homework 0 is important. It's due March 4th. This is basically information about yourself. Essentially, all future grading is predicated on homework 0. This is basically very simple. It's not really a homework. It's information about yourself, basically. We need to know more about you. And if you don't submit it on time, we cannot schedule you for a presentation. So please, if you don't want to take this course, please decide that as soon as possible, because there's a waiting list for this course. We cannot, unfortunately, take more than 22 students, because I would like 2 students to present each session, and we have 11 sessions. So if you drop the course later on, basically you're wasting some valuable slot for someone who may be interested in taking the course. So I'd recommend, if you're not interested in this course, please drop it immediately right now if you're going to do it. And consider that this is going to be a lot more work than other seminars. So if you have some other seminar you're eyeing, or if you don't need to take a seminar, please don't do it. I mean, if you're, of course, genuinely interested and if you want to participate, then take the course by all means. But if you're going to going to drop it, then it's not nice, let's say, for other people who are on the waiting list. And several of them have indicated that they're really interested in taking the course. Okay, so paper review preferences. Basically, we'll come up with a list of papers that you will be able to choose and rank from. So this will be due in due time. We didn't really prepared yet. So you're going to check the website and Moodle for instructions. And this is going to be important to submit on time. Otherwise, we cannot schedule you for a presentation. Okay, so let me give in the remaining time, let me talk about how to deliver a good talk, because it's going to be important for the rest of the seminar. So let me give you the one slide anatomy of a good paper review or talk. It's the same thing, I think. Whenever you're reviewing a paper and writing comments or giving a talk about a paper, I think it's very simple. First, basically, give the titles, authors, and venue where it's published clearly in the first slide. Then provide a summary. This could take multiple slides, of course. I'm going to give you examples of this in the next couple of meetings, example talks, basically. Summary is important so that everyone understands what's going on. And summaries really needs to be structured. What is the problem the paper is trying to solve? What are the key ideas that the paper brings about in terms of that problem? What are the key insights that the paper brings about? What are the key mechanisms of the key ideas? What is the implementation? So you go into a little bit more detail in the key ideas. What are the key results? And what are the key conclusions? Of course, you need to go into a little bit more detail when you present so that other people can understand these things. So summary takes some time. And then the critical analysis part starts. You first talk about strengths. What are the most important parts? And every paper has a strength, even though it may be the terrible paper. It may be a terrible paper. It still has a strength somehow. And I would encourage people to find strengths. Does the paper solve the problem well? Is it well written? And you need to order. It's best to order the strengths from most important to least important. For example, if the paper is really the first paper, seminal paper that opened the field, and then later everybody really worked on the field, then that's a big strength compared to the papers written well, right? So I would encourage you to think about the importance order of these strengths. Weaknesses, again, this is very important, and this is where you really need to think critically about, because strengths are usually proposed by the authors in the paper sometimes, in well-written papers at least, but weaknesses are usually not proposed by the authors for, let's call it a publication bias, right? Because they may be working on the weaknesses, or there's usually a bias in the publication system that tries to discourage people to talk about weaknesses, which is unfortunate, but that's how it is today. So, and we're trying to change the system, but it's not an easy system to change. Let me put it that way. And this is where you should think critically. Basically, every paper and idea has a weakness. This doesn't mean that the paper is bad. It means there's room for improvement, and future research can accomplish this. In fact, some of the seminal papers have some critical weaknesses, or some things that could be considered critical weaknesses, but they're not so critical to prevent the idea from being exposed. Like evaluation may not be up to par. Yes, it's a weakness, but is it really that bad to actually prevent the paper from being exposed? Sometimes it's that bad, right? Sometimes without an evaluation, it's not clear what the idea brings into the table, right? Then I think that's a big weakness. But sometimes it's kind of obvious what the paper brings into the table that's new without an extremely comprehensive evaluation. Usually you need some sort of evaluation to prove your point, of course, right? This is science in the end. But you may not need an extremely extensive evaluation because no one else has done it, something like this, for example, etc. So basically, this is where you need to think critically, and you need to, again, sort it based on importance. So if there's a fatal flaw in the paper, in the idea of the paper, for example, then that should be the most important weakness. If there's an issue in the evaluation that's problematic, but it doesn't affect the idea, that's not as important. Writing issues, if they're extremely severe, it could be one of the most critical weaknesses, but if they're not so severe, they could be mentioned, but they're not the most important weakness problem. Okay, and then the next step is thoughts and ideas. Can you do better? Present your ideas. So you can actually talk about your ideas over here, maybe potentially integrate it with the weaknesses, but after the weakness, it may be better. And then takeaways. What have you learned? What did you enjoy? What did you dislike? This is your subjective evaluation of the paper. And then you provide some discussion starters and questions so that people who are following your talk can discuss new ideas. And this is going to be important. You're as a presenter, you're also a discussion leader. So we are going to expect discussion leaders to actually start the discussions and ignite the discussions. Okay, and this review should be short and concise. Let's say 20 minutes or less than 1 page if you're reviewing papers. If you're taking computer architecture, you know that you've done these reviews in a similar manner. So this is my suggested paper discussion format. So spend about 20 to 25 minutes in the summary, spend about 10 minutes in the critique, and spend about 15 minutes or longer in the discussion, right? And this is the previous slide summarized over here, if you will. I'm going to talk about this more, of course, when we discuss. Okay, there's more advice. When doing the paper reviews and analyses, be very critical. This is where you could exercise your critical thinking. Always think about better ways of solving the problem or related problems. Also question the problem as well. Sometimes you may find that your questioning leads you to nowhere because the problem is very solid, right? Sometimes you may find that the problem is not as solid. There are other problems that need to be solved before this becomes a problem potentially. So read background papers, both past and future. This is where your mentors could be helpful. But today you have access to technology where you can find the background papers relatively easily. Sometimes looking at the reference list of the paper, if the referencing is properly done, it could be immensely useful. Of course, future, you can find it also by searching for the paper. You can find future papers that cite that paper, for example. Sometimes, unfortunately, if referencing is not properly done, future papers don't cite that paper, even though that's a seminal paper. That also happens. And but there your mentors could be helpful also. So this is how things progress in science and engineering or anywhere, and how you can make big leaps basically by doing critical thinking and critical analysis. And we have a few sample text reviews provided online, but we also have sample lectures that are going to happen. But if you're not patient, you can also look at sample lectures from the past incarnation of the seminar, which is last semester, actually, fall 2020. We actually have several example lectures over there. And in the past incarnations, there are even more lectures. Okay, so I will also mention that try to avoid rat hole discussions. This is actually important. And I borrow this picture from a book that I really like a lot, Performance Analysis of Computing Systems. Well, you're going to see that book, so I butchered the title probably at this point. But basically, there are some rat hole discussions that happen. You can always question the workload that's analyzed in the paper. You can always question the metrics. You can always question the experimental configuration. And you can always question the details here and there. And these may lead to rat holes that are endless. And I think our goal in the discussion should be elevate ourselves out of these rat holes so that we can discuss more consequential, bigger issues, as opposed to getting stuck in these rat holes, where the rats get stuck in the rat hole and they keep turning around in the rat hole without being able to escape because they cannot think better, right? So that's the idea over here. And this is, well, I guess this is the title. Yeah. How did I forget this title? Because it's a beautiful title, right? The Art of Computer System Performance Analysis. That's the book. And I recommend this book to people. And this is the real picture in that book from a section. And I'm going to read some of this because I think this is really important. And this also points out the importance of this sort of course in your broader life. So this is not just about scientific presentations. It's about any presentation that you do where there's a decision maker and you're trying to convince the decision maker somehow. Basically, even if you present correctly, even if you do the performance analysis correctly, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. The list shown in box 10.2, which is the next page I'm going to go to next, is a compilation of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. And also the list is helpful in getting the competing proposals rejected. So this person clearly has a sense of humor, right? And then he goes on to say, there's no clear end of an analysis. An analysis can be rejected simply on the grounds that the problem needs more analysis. This is the first reason in the box 10.2 we will see. The second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environment can always be questioned, etc., etc. I'm not going to read more, but you can see this box over here. It's about 26 items over here. Like, this needs more analysis. You need a better understanding of the workload, blah, 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 blah. It requires too much state. This is not simple. And then there's it's too simple somewhere over here. It's too deterministic, etc. This impacts hardware. Clearly, that's a software-minded person. That is beyond today's technology. It's a funny thing. Clearly, that's a short-sighted reason. And why change? It's working okay, right? I think this is a very negative look at the world. But you will see this sort of decision maker. Why change? It's working okay. Why should I follow science? It's working okay for me. Yeah. Anyway, so I'll give you more advice on talks, and I will recommend you to take a look at my past colleague, Keyvan Fethahalian's tips for giving clear talks, because I actually subscribe to a lot of the things that he says over here. There are many useful and simple principles. I'm going to copy and paste some of them. Every sentence matters. The audience prefers not to think. You just need to drive the audience to your point. Surprises are bad. Say why you are going to say something before what you're going to say something. So high level is much more important than low level details. So basically provide the goal first, provide a high-level overview, and then go into the details. I see too many papers written exactly the opposite way. They jump into, oh, this is our mechanism. Why do I care? You didn't even tell me your goal, right? Okay, you told me your goal, and then you jump into your mechanism. Again, there's a problem. You should have given me an overview of your mechanism, how you're going to do things before you tell me your mechanism, because I don't have the right abstraction level, right? So abstraction level is really important when you're writing papers and delivering talks. If you don't follow the abstraction level that's logically enabling the reader to understand something, then you have a problem in both your writing as well as giving talks, right? So why is very important, then much more important than what first. And also what at a high level, this is the key idea, is much more important than this is my implementation. I don't care about your implementation until I know about key idea. I don't care about your mechanism until I know about your key idea. And I don't care about your key idea until I know about your goal. So keep things that way. If you keep things this way structured, then you can actually write much better as well as talk much better. Okay, and then explain every figure, graph, or equation. This goes without saying, maybe. And when improving the talk, the audience is always right. Well, if the audience is listening, they're always right, of course, right? There's something that needs to be said over here. Sometimes the audience is not listening. As a result, they may not be always right. If the listening is not caused because of some fundamental flaw you have in the organization, then audience is probably right. Okay. So let me give you some examples. So who painted this painting? Unfortunately, we're going to take a little bit more time than I expected, but you feel free to drop off if you have something. You can watch this part on YouTube recording later on if you have something to do. Basically, I'm going to cover the course logistics a little bit more, but I'm going to give you some more advice on how to best approach this course. So that's what you're going to miss, but you're going to easily be able to find it online. Okay, so the person who painted this painting is Salvador Dali, who is clearly a famous painter. But this is not what you expect from Salvador Dali. Well, this is not Salvador Dali, first of all. He painted someone else. I think it's Luis Buñuel. But basically, this is a Dal painting, which is realist, right? Which is not what Salvador Dali is famous for. But there's a point here. He did this before he broke all the rules and did something like this. So this is the Burning Giraffe, one of his, well, he has many famous paintings, but this is one of his famous paintings, right? You can see that he painted this later, and he himself is a little bit different also. But you can see this is breaking all the rules, right? I think at that time, at least, it's only Dali who was painting this sort of painting. But even Dali started by following the rules. He figured out how to do these things really well before he did things that are, I mean, some people consider it crazy, but crazy is really the good art, basically, as you can see, right? You can interpret many things over here, whereas your imagination is much less here, in a sense, right? So basically, he did not break the rules immediately. If he did, maybe he wouldn't have been Dali. And I will encourage everyone to actually think about it when they're actually doing presentations and writing papers also. There are very well preserved and well-tested guidelines in terms of doing presentations, writing papers, especially technical papers, of course, and technical presentations. And if you follow them initially in your first presentations, you're much, much better off. If you do something like this, well, you haven't experienced what following the guidelines are so that you could break it in a way that Dali could have done. Okay, so the takeaway is learn the basic principles and follow them before you actually get to a point where you can actually consciously choose to break them. Actually, I was debating whether I would put the can over here or may over here. Clearly, you can do it, right? You can break it, but maybe you will not be able to have a good mileage from breaking it. And I actually tell this to my graduate students who are writing papers also. But basically, you can anyway do it, but it may not work well to your favor. So basically, that's why I chose can, because it's a choice that you make. But I think I would rather recommend that making this choice much earlier. So if you, I actually can attest to this. Like I have a very well-defined methodology in delivering talks and presentations and also writing papers. And over time, it has evolved. Initially, I was, let's say, more dull, like this painting. But I was following the rules and I was learning. And then later on, I was more consciously choosing to break the rules. And sometimes if you know exactly what you're doing, and if you can fix for it later on, then you can actually consciously choose to break them. I see sometimes too many cases where presenters or some writer writes in such a way such that they break the rules, but they also have no provisions to fixing them. So in the end, what's written or what's presented is a huge mess. And most people cannot understand it. And even though there might be a great idea in there, no one is able to decipher what that idea is. Okay, so with that, let me talk about how to participate also. So basically, how to make the best out of this course. I would suggest coming prepared. Of course, there are a lot of papers, and it's hard to imagine that everyone reading the paper and critically evaluating them to the level that the presenter is doing it. But I'd encourage as much as possible doing that. Read the abstract, read the intro, read the conclusion, if you cannot read anything else. Think new ideas as much as possible. Bring discussion points and questions. Read other papers if you can. Be critical. Brainstorm and be open to new ideas. Pay attention and discuss and contribute. This is important. And participate online before and after each meeting. So online participation before is also allowed. I mean, the goal of this course is really to enable you to become better critical thinkers and presenters. So if you want to discuss something earlier, you can feel free to use Moodle, for example. So we're going to enable some Moodle forums to enable that. But after, clearly, I would recommend people to participate. That way you can get a lot more out of this course than what you will get. So let me give you a guided talk preparation a little bit. So basically, preparing a talk is an algorithm. You first check your presentation date. We're going to assign that. And then you study your paper and other papers also that are related. You create a draft presentation. And then you meet the advisor, meaning mentor, and get feedback. In this case, we have 2 advisors, 2 mentors. And then you basically keep repeating this loop. And then you will present after some point. So preparing a good presentation takes time, so start early. So studying your papers is important to do it carefully, critically, and creatively. So basically, be very careful, understand it, look up terms, possibly read cited papers. I'd recommend reading papers. Do it critically, find limitations, flaws. Do it creatively, think of improvements. If a paper is old, figure out that if it has had impact or other papers have built on it. Think of your own improvements. If you can, try examples by hand. Sometimes you will see source code. Try to do it. Try tools if they're available. And consult with your mentors if questions, and also the lead TAs if there are questions. Usually mentors are your first contact point. Okay, when you create a draft presentation, as I discussed, we already discussed how to do it. I'm not going to go into the details of this, but this is the draft presentation that can help you, but follow the recommendations that I discussed earlier. And then once you have the draft, meet your advisor. So prepare for the meeting. It's your responsibility to schedule them once you know who the advisors are, but they will also ping you. Send slides in advance. Write down questions in advance. Make sure you address their feedback. Take notes in the meeting. And meetings are mandatory. So we have at least 2 meetings, and these should happen at least 1 week before the talk. So the schedule will be a bit tight for the first presenters, and we're going to take that accordingly into account. But the schedule will be much more relaxed for later presenters. So basically, do not get to your mentors the last week and say you want feedback, because at that point, I think you probably don't deserve the feedback, although mentors will be nice enough to actually provide the feedback, I think. Anyway, don't deserve a lot of feedback if that's the case. Okay, let me talk about grading also, even though I think grading is hopefully not the real reason you're taking this course. Because if the grades are your goal, I would recommend you to take, if the grades are your only goal, I'd recommend you to take some other seminar that is easier, frankly, than this seminar. Clearly, the seminar requires more work. But of course, as I mentioned, it's high investment and also high return. So hopefully grading is not what your goal is. And if you actually have the right mindset, you'll actually do really well in this course by not even caring about the grades, but caring about doing the things right. Because I think everything you do in this course is going to be useful in your future life, because you will be delivering presentations, you will be creating ideas, you will be evaluating ideas, you'll be basically on one side of the roles that we have in this course, or both sides of the roles. I would tend to argue that you will be on both sides of the roles, whatever you do in future. Okay, so quality of your presentation is important. That's a good chunk of your grade. As you see, clearly there are many aspects of quality. Again, we will take into account the difficulty of the paper and the time you had to prepare also in this grade. But in general, a quality presentation is something that you will also get to learn about in this class, I think, if you haven't already. Quality of the final synthesis paper is also important. That's a good chunk of your grade. And this is the written form. You can find it out online. There's attendance and quizzes, 10% of the grade. And there's an additional participation, which is important because it gives you a bonus points. Basically, it'll make up for any losses that you may have over here. Basically, did you ask good questions? Did you participate and contribute to the discussion? And I think I would recommend doing that regardless of what grade you may get, because it's just fun to do that. And last semester, for example, even though last semester we had this course online also, well, I guess the initial lecture was not online, but everything else was online. Maybe initial 2 lectures, I don't remember. No, last semester it was fully online, fall 2020. I'm talking about spring 2020. Last semester, fall 2020 was fully online. But the experience was actually quite good because people actually participated a lot over Zoom. And I would recommend participating a lot over Zoom. And I would recommend actually people talking and turning on their videos so that we can have a much more live experience. I'm going to talk more about that later when we start presenting. Okay, so we will also try to give you feedback. We recently discussed the strengths and the weakness of your talk in class. I mean, we haven't been as diligent about this because we didn't have a lot of time after the discussion. Let us prefer upfront if you don't prefer us to give feedback, or remind us if you want feedback after your presentation, because sometimes we forget to give feedback, at least in the live session. So please let us know. In the past, we have not been as good as providing this sort of feedback, unfortunately, because we didn't have a lot of time, I guess. So somebody said, is it a requirement to have a webcam then? I think I would strongly suggest that you have a webcam if possible, because I think that will enable a much better interaction in the class. And in fact, the feedback we received from past students who've taken the course, like last semester, is that it's much better if we actually see the people who's talking for sure, but also the participants, so that they can have a much better experience. And we're a small enough class to enable that. Like, we're not going to be more than 40 people at any given point in time in exceptional situations, basically. So whenever you're asking questions, for example, enable your microphone and webcam and ask the question. Last time, for example, even though the discussion was really good, there's room for improvements. Basically, we could have had more live interaction, if possible, of course, right? Such that people could ask the questions, because it's kind of dull and odd if people write questions on chat and other people go through the questions. It's a lot more interactive if people ask the questions in voice and they're visible while asking the questions. Okay, and then you can arrange a meeting with your TA to get feedback clearly about the presentation that you have delivered. Okay, this is the expected schedule. So we will meet once a week with 2 presentations per session. Next meeting is next week, yes, but you're not going to be presenting. Your presentations will start on 11th of March. So there will be 22 presentations in total. Each presentation is 50 minutes, including questions and discussion. We tend to overrun, unfortunately. I mean, the feedback on that is mixed. Most people say, complain that we tended to overrun, but they say the discussion was very valuable. So I don't know how to make of that. I think I would err on the side of knowledge in general, based on my philosophy, than enforcing strict limits, because sometimes if we enforce a strict limit, some discussion that would otherwise be extremely useful potentially in the long run is really curbed. Anyway, we're not going to run a whole lot, hopefully. But if you are not interested in taking this course, please drop it right away, because so that other people can take the course. I'm going to remind people again. So paper assignment will be done online. Study the list of papers we're going to upload, and check your email, and please be responsive about that. So homework zero, as I mentioned, it's an information about yourself. So this is due March 1st. And please submit it on time, as I said earlier. Paper review preferences, you're going to get an email through Moodle, and we're going to also post on websites so that you can provide us with your preferences and ranking order of the papers that you are interested in presenting. Again, if it's not submitted on time, we cannot schedule you for a presentation. So please do submit it on time. Wow. So we were able to cover everything, but we did take longer than expected. So sorry about that. but hopefully we've answered a lot of the questions that you may have had so far. So if you have some other questions, burning questions, please feel free to ask right now. Let's see, I don't see anything. And you can actually unmute yourself and ask as well, if you think that you're going to ask a question. Okay, I see something. Is it okay to ask questions not directly related to the course? Okay, I guess, sure, go ahead. If no one has questions related to the course, you can ask it.
Okay, so can you hear me?
Yes.
Okay, so this might be a funny question, but I was just wondering if there's any reasonable way to get a hold of any of these new technology samples, I guess. For example, those in-memory processing things, to toy around with them, because it just sounds like so much fun, but I don't have the backing of a big institution.
Yeah, sure. Well, I think that's a great question. So yes, but I think you need to be working with a research group that has access to them. So for example, the UPMEM infrastructure, we have access to it, and we have been running experiments with it. Juan is actually leading that effort. And if there's some interest in working with that infrastructure, and if there's a good plan we can enable you to get access, of course. And in fact, in the past, people who've taken the seminar or DDCA or our other computer architecture course who are interested in doing that, some of them are now working with us and they have access. But if you directly contact the company, my guess is you may not directly be able to get access to it. Of course, if you pay them a lot of money, maybe you will. So that's my take on it. So Samsung's infrastructure is a bit too new. It's a bit more difficult to tell who they will provide access to. But in general, that's how these things work. Usually, they provide samples to researchers who are working in the field, or at least enable access so that they can enable access to hardware. And then these researchers evaluate and provide feedback to them. So that's the benefit that the companies get by enabling that sort of access, because these are not real products yet. Although UPMEM is going to, I believe, if you have enough money, you can also buy these products from UPMEM, for example. I don't know about Samsung at this point. So hopefully that answers your question.
Yes, thank you very much.
So there's a path, basically. I think at ETH, we clearly have access to them. So if you're really interested, just let us know. But not everything, clearly. Some other things we may not have access also because they're just too new. And it needs to be negotiated also with the companies. Okay. But that's a good question. I think I would consider that related to the course for sure. Clearly, it's not within the course, but if you're taking this course, hopefully you have some interest in this sort of research, and that's a good question to ask in general. So any other questions? I don't see anything on chat. Nobody's speaking up. So I'm not going to take the YouTube questions. Maybe someone can actually in the next time copy and paste, or maybe we can look at those questions afterwards as well, and then try to. Okay, there's somebody. Okay, Robert, thank you for copying and pasting it. Okay. To get accepted for a collaboration work with your PhD students in your group. Okay, that requires application to our group. I guess there's how likely it is. I don't know. Yeah, basically, I think to be able to do that, you need to apply to our group. Especially, I assume this is coming from someone who is outside of ETH. Certainly, we have an application site for my group, and we have a also methodical way of applying. So I would suggest applying through that and letting us know that you applied. That's the really only way to start collaboration with my group outside of ETH. Within ETH, of course, you have a lot more opportunity, right? Okay, Juan posted the application site. You can post on YouTube also, Juan. I'd recommend because I think the question actually came from YouTube.
Sure, let me do it.
Yeah, But at ETH, if you're at some point, we will probably discuss it. But at ETH, certainly you can do bachelor's thesis, master's thesis, and then you can do semester projects, etc. So at ETH, you have a lot more opportunity to be able to do that clearly and obviously. That's how it should be, right? But if you're outside, you have also opportunity, but we need to evaluate you through that application. And the second question was, could you please tell me how often you would be on live sessions? So it depends, I think. So we plan to live stream all of the digital design and computer architecture lectures this semester. I'm not sure about the seminar. So for seminar, I think, I think we will need to discuss so how comfortable the presenters are. I'm certainly very comfortable, right, presenting publicly, but some presenters may not be comfortable presenting publicly for live streaming on YouTube. So we may need to have closed sessions. In the past, we always had closed sessions. We never posted any presentations on YouTube, even after the fact. But I think it's probably a good idea to ask the individual presenters. So Mohammed and Juan, we should really prepare a survey for that and ask individual students to basically say whether they're comfortable being on YouTube live streamed. It could be good, right? You get more feedback that way. But it could also, I understand that you may not be used to public speaking of that sort. So that's also fine. So there's no requirement in the end. We will go with the presenter's choice. Okay, any other questions? Burning questions? Okay, I don't see any other questions pasted from YouTube also. So in the future, we'll try to handle them better, maybe. Okay, another question pasted, I guess, also from YouTube. For something like genome sequencing, why can't we exploit cloud or data centers for the same instead of having mobile nano devices? So, okay, this is a good question. So you can, but now you're subject to all of the inefficiencies of moving the data from your device to the cloud and data center, which is a lot of overhead in the end. So that's what's happening right now, actually. Nanopore sequencing, for example, people sequence their a lot of genomes and they send it to the cloud for analysis, and the cloud responds 2 weeks later, or I don't know, a week. Or if you parallelize your program nicely, maybe a day. Fine, you can do all of that, but now you're sending a lot of data. So you're basically eliminating all of the low latency benefits that you could get by the device, within the device, and also energy benefits that you could get. So basically, there cloud processing is certainly an option, and maybe it's a good option for some cases, but not in the cases that I think are going to be extremely critical in terms of latency and energy. In fact, there's a really good talk related to this. Edge computing, there was this keynote talk by Satya, who was also my former colleague at Carnegie Mellon. He's a professor in distributed systems at Carnegie Mellon. And he works, he pioneered a lot of concepts in distributed systems. Right now, he's working on edge computing. And he delivered a nice keynote talk at the SysTor conference in October 2020 on edge computing and its importance and what you can do on the edge that you cannot do on the cloud. And he has a lot of example applications that require very low latency, very low energy, security guarantees, privacy guarantees, etc. And all of those get broken if you actually ship the data to the cloud as opposed to doing it on the edge. So maybe someone can actually paste that talk to the link, paste the link to his talk. This is Satya's talk. I would recommend people to watch it. Actually, I delivered a keynote in that conference on intelligent architectures for intelligent machines, and he delivered a keynote on edge computing systems. And I think that's a very insightful keynote talk. And basically, I think in the end, if you're moving the data, you're basically fundamentally less energy efficient, fundamentally lower performance potentially. You can of course exploit the properties of the cloud, but you're moving data. You may need to move a lot of data to the cloud first. Fundamentally, you're giving up some privacy and security because you're moving it somewhere, and somebody can eavesdrop on the channels where data is moving on. And clearly, cloud may not be trusted, right? Clearly, we're having a lot of issues today with some of the bigger cloud providers which makes us question, is it really good to actually trust these providers? So basically, I think cloud is not a good answer overall. Of course, it has its role, but I think pushing the computation to the edge device has a lot of benefits as well. Okay. Okay, I think I saw one more question. I will take that and then we will conclude. I saw this from YouTube also, now that I can see my YouTube finally. What is the prerequisites for taking this class? What do you suggest for online listeners? So for the seminar class, I think prerequisites, I mean, I guess in the end, there are no prerequisites. As long as you know computer architecture, you've taken a class in computer architecture, you followed my lectures, I think you should be comfortable with this. But again, it depends on whether you publicly make the lectures available. But I think if you're taking digital design and computer architecture or other computer architecture courses online, I would recommend doing as much as possible what we ask students at ETH to do. If you're an online student, and I know that there are a lot of online students because some of these classes are actually used in some universities sometimes. Sometimes people are using it to supplement their own courses. I know that some students are using it to prepare for interviews, for example, etc. I'd recommend doing as much the same things as possible as we ask the students who are actually enrolled for the class at ETH to do. I think that's the best way for learning. So read as much as possible. And yeah, clearly we don't have the capacity to enable folks to present, random folks online to present. I don't know how to do that exactly. I'm not sure if even the MOOCs are doing that today. That's a different thing. Maybe there's a MOOC designed for seminars, but I'm not sure if I know that. Okay, so I think that's the last question I took. I see Juan posted Satya's talk. Maybe you can post on YouTube also. Okay, so it doesn't look like there are more questions. So I think I'm going to skip at this. I'm going to finish at this point. And I will see everyone next week. And we're going to cover some example seminars, how to deliver a seminar, essentially. Okay, take care.